So I told you that shifts in that curve, either right or left, means that we have a change in affinity of hemoglobin for oxygen binding. So factors that can do this by changing hemoglobin structure, which really makes sense, right? At any given partial pressure of oxygen, which is the main determinant of oxygen saturation, at any given PO2, the ability of oxygen to bind to hemoglobin is going to depend on the structure of hemoglobin. It's a chemical reaction. So we have other things that can alter protein structure slightly. One of those is pH. That can alter affinity, which is binding affinity. So PO2 is the biggest thing, right? That's one of the variables in this curve. That's the x-axis. Other factors besides pH are going to be temperature. I'll just list them here. I'm going to show you two examples. One's temperature, one's pH. PCO2, BPG. This is a byproduct of glycolysis. So given that, it'll make sense why that's, it should make sense that's going to be present in active tissues. So a temperature change. I think that's, yeah, I have pH. Okay. So let's look at one of these. We're going to look at pH. So here is, what is this? What's normal? Well, I'll tell you, normal blood pH is between 7.35 and 7.45. So this is our normal. This is the oxygen hemoglobin saturation curve in purple. That's kind of our normal that we drew in the previous slide. Now we've got shifts. So remember I said before, our example was a shift right. So let's do that first. This shift right is low pH, right shift. What does this mean? Lower affinity. Release more oxygen. Lower affinity means less oxygen bound. It's going to be releasing oxygen, not binding it. This is called the Bohr effect. PCO2, high PCO2 is the same thing, right shift. And actually those go hand in hand, high PCO2 and low pH. And we'll see that relationship in just a moment here. Another video. This shift right is due to, again, the change in structure of that hemoglobin, reducing affinity for oxygen. And this is called the Bohr effect that is going to enable oxygen unloading. So unloading. This is useful because active tissues tend to have high PCO2, low pH, and need oxygen to unload onto them because they're active. And then the opposite direction, the opposite is true. So a higher pH, an increase in pH is going to mean higher affinity. So this is going to increase loading and would be due to the opposite. So low PCO2, high pH. This is very relevant for our exercising muscles, releasing more oxygen. This right shift, this is the Bohr effect. Can either be due to low pH or high PCO2. Other things can shift this curve. I already told you this. Here's temperature. So similar idea here. Here's body temperature. And then we've got kind of two extremes here that your body wouldn't really be at, but to show the example, a curve shifting right means releasing more oxygen. Hey, when our muscles are exercising and we start producing heat, this is going to help our body release more oxygen into those tissues. So this also makes sense. One of those to make sense of, right? Anything where you're going to want to have more oxygen delivery occur is going to be a shift right, which means resulting in releasing more O2. Opposite, release less. This is an oxygen hemoglobin dissociation curve. Here's our adult hemoglobin. This is our normal curve, S-shaped, etc. What is up with this fetal hemoglobin? So, right, in a fetus, the hemoglobin that's made, what's up with this left shift? And does that make sense? Left shift, what does that mean? That means increased affinity. Increased affinity, increased binding. So it's going to bind oxygen more easily than adult hemoglobin is. That's pretty useful for the fetus, really a parasite. It's as oxygen is pumped throughout the mother's body, the way it gets to the fetus is through the blood supply through the placenta. The fetus does not have lungs. So in order for the fetus to get enough oxygen, it's got to go from the adult to the fetus. It's got to be a higher affinity in the fetal, for the fetal hemoglobin for oxygen transfer to the fetus. That's an important example of a left. It's not really a shift. I guess when you are born, you have a right shift. Probably some cool differential gene expression there related to the different hemoglobin proteins that are made.